Let's continue with the course. So we are in lecture 20. So we came a long way, and today we're talking about, again, optimization. So finding minimum, maximum points of the function. And then we're going to look through a plan how to analyze a function using derivatives. So maybe I can give you a certain function, and I'm asking you to understand where it's increasing, decreasing, where are the critical points, where the function is convex, concave, and then based on that information, we see how we can sketch the graph of the function without using any software or without doing anything very complicated. Okay, all right, so in the last class, that's exactly what we talked about. So we talked about derivatives, and we talked about the ways to apply derivatives to specific functions. So for instance, when a derivative is positive, then we know that function is increasing. So for these values of x for which the derivative is positive, the function increases. Vice versa, for the x values for which the function or the derivative of that function is negative, the function decreases. And then when we are at 0, when a derivative is equal to 0, then we learn that the function neither decreases nor increases. And in fact, this x that we call x star, a specific point which forces the derivative to be equal to 0, is called a critical point or stationary point. Because it makes sense. The function neither increases nor decreases, so it evens out, it stabilizes in a way. And then we learn that the critical points actually indicate a location of so-called local maximum and minimum points of a function. All right? And then how to classify whether critical points indeed give location of local maximum or minimum, then we look at second derivative. So second derivative is just a derivative of a derivative. If you know basic rules how to take derivatives, you just apply again by taking derivative of a derivative. And then if the second derivative is positive for a certain set of x values, then for those values the function is convex. So you should imagine that the graph has this shape of a smiley face. If it's negative, the second derivative, then the function is concave. So again, just to make association, then the function has this sad face behavior. And then we can actually use the second derivative as a test to classify our critical points. So whether these indeed give location of local maximum or minimum. So we take the critical point from the previous step, solving where derivative is equal to 0, and we plug them into the second derivative. And if indeed the second derivative at that point is positive, then we know that around that critical point, the function is convex, meaning that we are at local minimum. Vice versa, if the second derivative at that critical point is negative, then we are at local maximum. So this is the picture that we analyzed last week. So this is a cubic polynomial function. It goes like this. And then the important bits were these. So we have x star 1 and x star 2. So these were the critical points. And we see that at these points, the tangent lines have slope equal to 0 because they are flat. So this means that derivatives at these points are equal to 0. So therefore, indeed, x1 star and x1 star and x2 star, they give critical points. And then we can check second derivatives at x1 and at x2, and we will find that one is negative, another one is positive, meaning that around x1 and x2, the function is respectively concave and convex. So this is how concave function looks like. This is how convex function looks like. So we see that around x1, there is the sad face going on. Around x2, there is a smiley face going on. And clearly then we have a peak here and a bottom here. So we call these local maximum and local minimum. And they are only local because, well, just looking at this function, it's very easy to spot that this function does not have clear maximum. That is, if we go along the x-axis, the function just increases. It never stops increasing. So clearly there is no maximum. It goes to infinity. At the same time, if we keep on going to another side, if we just keep on inserting negative x values, the function just goes to negative infinity. So we cannot tell anything about global maximum or minimum with calculus, meaning taking derivatives and doing second derivative tests, unless we are at a very special case where the second derivative does not depend on x values anymore. Right? So in last lecture we had x squared. If we take derivative 2 times, the second derivative is equal to plus 2. It does not depend on x value. So therefore, very clearly, it does not become convex or concave depending on where you are on x-axis. On the other hand, here, it's very clear that for some values of x, the function is concave, and then it turns into being convex. So if you are in this situation where the function varies, whether it's convex or concave, then we're going to have local maximum or minimum. And then most likely function is just going to go to infinity or minus infinity. All right, so we, by taking derivatives and implementing second derivative tests for classification of these stationary or critical points, we pick up local maximum or minimum. So we need more information to understand whether there is global maximum or minimum. Okay, so that's, and we went through many examples in taking derivatives and so on. So what we're going to do today, we're going to continue with the examples. So we're going to explore several functions, and then we're going to see how to find critical points, how to take second derivatives, how to classify them. And then we're going to go through one particular example where we will do the full analysis of a function. I'm going to give you a function, and we will take first derivatives, second derivatives. We will find where the function is increasing, decreasing, where it's convex, where it's concave, and where is the global minimum, local minimum, local maximum. And then we will try to sketch the function given the information that we gauged along the way. All right? But before that, I just wanted to very quickly talk about tangent line once again. So it was the last exercise in your exercise set from the book for this week, but I didn't have enough time to actually to actually cover this topic. So very briefly, before we go into these two very, very important, this is important too, but it's way more straightforward what to do. We just need one formula. So the question is this: finding the formula for the tangent line. Right, so we know how to find the slope of a tangent line at a specific point. It's just a derivative of a function at that point. But once we know the derivative, how to find the function for the tangent line, or formula for the tangent line. So, for instance, here I'm going to give you a picture. So here I have a function and I have a tangent line, right? So in here, let me make it even a bit bigger, perhaps like this. So here I have a specific function here, 2x to the power of 3 plus 2x plus 5, and that's the blue line. Okay. And then I have a function 8x plus 1, a linear function, the orange one. And I made it in this example such that this orange line is a tangent line at point x equals 1, right? So given that I know this function, and let's say I want to know the function for this orange line. In this case, I gave it to you, it's 8x plus 1. But how could I find it? I'm telling you, I have this blue function, this one, and I want tangent line to just touch the graph at x equals 1. how do I find that this orange line is given by 8x plus 1? Right? So how do I find equation for this? And for this, you only need one formula. So let's go through a particular example, and you will see that it's very straightforward as long as we apply one single formula. So that's the question for this example. How to show? So how to show that an equation for the tangent line at x equals 1 is 8x plus 1. So how to do that for that specific function? Well, we need a formula that I'm going to give you. And the formula is this. Y equals f at a specific point A. So I'm going to tell you what this A is. Plus derivative of that function evaluated at A. And then I do x minus A, like this. So that's a formula for a tangent line at a specific point. And that point is A. So in this case, in our example, A is equal to 1. So in our example, A equals 1. So in other words, I'm interested at a tangent line at this point, 1. So I'm going to put 1 in here instead of A everywhere. And then I'm going to take the function, evaluate at 1. I'm going to take the derivative of that function, evaluate at 1. And I'm going to multiply it by x minus 1. So I'm just inserting 1 right here. So let's apply this formula to our example. So in our example, we just need to match the numbers. So in our example, what I need to do first, I need to evaluate f at 1, right? So I need to insert 1 into the function. And my function was 2 times x to the power of 3. So 2 times 1 to the power of 3 plus 2 times x, so 2 times 1, and plus 5. Right? I'm just inserting the point I'm interested in into the function. So that is going to be 2 plus 2 plus 5 equals 9. So now I know that for my specific function, this one, 2x to the power of 3 plus 2x plus 5, I know that at point 1, this is going to be this part in the formula. So we can in fact connect it so that we computed this part right here. Now I need to find the derivative of this function, and we can always find the derivative. So that was step 1. Step 2, I need to find a derivative of this. So the derivative is going to be 6 times x squared plus 2. I'm taking a derivative of this function. 2x to the power of 3 plus 2 plus 5. So derivative of this component is 3 goes down, 3 times 2, 6, and then we subtract 1 from 3, 2. Derivative of 2x is just 2, and then derivative of 5 is just a constant, so it's just 0. So I just took a derivative of this function. All right, so that's the derivative what we got, 6 times x squared plus 2. And now I need to compute this part. So I just need to insert my point of interest into this one. So let me do it in the next page. So the third step, f prime, the derivative at 1, is given by 6 times 1 squared, which is just 1, plus 2. So that is equal to 6 plus 2 equals 8. Okay, so now we just plug everything together into the formula. Plug the numbers into the formula. Right, so I'm just going to repeat the formula. Y equals f at a, where a is equal to 1 in our case. Here's a plus the derivative at that point, and I have x minus. Okay, so now we just plug it in. We computed this part, that was equal to 9, plus we computed this part in here. So this part is computed in here. It's equal to 8. And then I do x minus 1, right? Because now a is equal to 1 right here. Let's use maybe red color for matching the formula. So I inserted 1 here. 8 is equal this part, and 9 is equal this part. So we computed these two separately, and we just plugged in 1 everywhere. Okay, and now we just need to multiply things out. So multiply 8 with x and multiply 8 by minus 1. So this is going to be 9 plus 8x minus 8. And this just gives x times 8 plus 1. And this is the result that we were seeking to demonstrate. That's indeed the orange. That's the orange line in the graph. So if I know a function, and if I know how to take a derivative of that function, and I know a specific point that I'm interested in, like in this example, I could have chosen any point really. I just chose 1. I could understand how the whole tangent line looks like and how it works. So in this case, I just preemptively plotted them together as if I knew the formula for tangent line at x equals 1 at this point. But then we verified that by using the formula, we actually got the same result. That there is this specific and very nice formula that can give you the tangent line immediately. All right, so now you can go ahead when you solve exercises and tackle the very last exercise if you didn't manage or didn't have time yet, or you were waiting for me to cover this. So the whole thing is to have this formula, take derivatives, and plug in the point around which you are looking tangent line at. Okay, so this was a little bit of a digression because I didn't have time to cover this formula in the last class. But now I wanted to continue with optimization exercises. So that's the topic 1. So I want to explore several functions, and I want to find local maximum or minimum. So I want to go through a few examples. So example A. So we have this function, 2 over 3 x to the power of 3 plus 9 over 2 x to the power of 2 minus 5 times x plus 8. So you have this function, and the question is, find local maximum and minimum. So give you the function, and I'm asking to find local maximum and minimum. So we know the recipe, we know that we will take the derivative, we will equate it to 0, we will solve for a critical point or points, then we're going to take the second order derivative, and then we're going to plug those points into the derivative to understand the sign, which gives us convexity or concavity around those points. And that's how we're going to be able to classify whether it's local or maximum or minimum. Okay, so we just follow the recipe, and we start by taking the derivative. So can you help me take derivative of this function? Again, because you can look at this function as a summation, or as a summation of several functions. We can just take derivative separately. So what is the derivative here? Exactly, this is just 2x, because, well, if 3 moves down, it cancels out with 3 in the denominator here. What's the derivative here? And I forgot power of 2. What is the derivative here? Yeah, I think somebody's saying it correctly. That's 9 times x. Because again, 2 moves here and it cancels out with 2 in the denominator. So that's quite convenient. And then of course minus 5, because derivative of 5x, or minus 5x that is just 5. And then derivative of this is just 0. So what we need to do, we need to equate this to 0 and solve for critical points. So we will need to equate this to 0. Okay? 2x squared plus 9x minus 5 equals to 0. So now, because the equation here is quadratic, because we have power of 2, then we can expect that we may have not even one stationary point or critical point, but we can have more. We can have up to 2, because this is going to have at most 2 solutions. Yeah? So we can use the formula. We can do x1 equals to minus b, so minus 9, plus square root of 4 times a times c. Sorry, b squared minus 4 times a times c. So b squared is 89, right? I need to do 9 squared, 81, minus 4 times 2 times minus 5. 4 times 2 times minus 5. So this is b squared minus 4ac. Right? C is minus 5. And I will divide it by 2 times a, which is 4 in our case. Right? 2 times 2, 4. Okay? Which means that I have minus 9 plus square root of 81 plus 40. Right? Because I have minus here and I have minus here, so then minus turns into plus. So I have 81 plus 40, that's 121. And I will divide it by 4. That's the first solution. Okay, so minus 9, and the square root of 121 is very nice, it's just 11. And I divide it by 4. So minus 9 plus 11 is 2, divided by 4. We have 2 over 4 equals 1 over 2. So one critical point is given at 1/2. Right? So we immediately see that we're going to have two critical points. One at 1/2, and another one, well, we just use the exact same formula, we just flip the sign in the middle. And x2 is going to be equal to -9 minus square root of 121, which is just 11, divided by 4. So that's going to be -9 minus 11 divided by 4, minus 20 by 4 equals -5. Okay, so we have 2 points. We have -5 and we have 1/2. So these points potentially give a location of local maximum and or local minimum. So the first step is done. We found the critical points by taking derivative and equating it to 0. But so now we need to understand whether these are local maximum or local minimum locations. So in the second step, we look at the second derivative. So we can remind ourselves that the first derivative was given by 2x squared plus 9x minus 5. So that's the first derivative. But now we need to find the second derivative. Second derivative. So what is the second derivative of this function? 2 times x squared plus 9x minus 5. Exactly. That's just 4x plus 9. Okay. So what we do now, we take both critical points and we insert into the second derivative to see the signs. So the next step is insert x1 equals 1/2 and x2 equals -5 into the second derivative, f prime x. Okay, so that's what we do. So we take the second derivative and evaluate it at 1/2, which is 4 times 1/2 plus 9, which is 2 plus 9 equals 11, and that's clearly positive. And then we insert -5 into the second derivative. So it's 4 times -5 and plus 9. So this is equal to -20 plus 9 equals -11. And this is clearly negative. So what are the conclusions that we can make now? Can you tell me which of these critical points, 1/2 and -5, which of these give the location of local minimum? Exactly, 1/2 is going to give the location of local minimum, and -5 then vice versa, local maximum. Okay, so that's what we found. So we can write it, that local minimum is at x1 equals 1/2. And to actually find that value, the minimum value, then you will need to insert the value into the function, right? So you need to take the function and you need to insert 1/2. So you need to take a function from which we started, this one, and you will need to plug in 1/2 everywhere here to actually get the value, because the derivatives, they give the location, and then once you find that location in terms of x, you insert it, and then it produces the functional value. So you can use calculator here, for example. That's not so important. this is going to be approximately, because all of these are fractions, these are going to be approximately 6.7, approximately. And then local maximum is at x2 equals minus 5, which means that if I insert minus 5 into my function, then again, all of these are fractions, so well, I trust you to plug in the number into the calculator. That's going to be approximately 62.2, approximately. So the little lesson here is, if I'm asking you to find local maximum or minimum, there are two steps to this problem, right? So you find the critical point, then you can classify critical point with a second derivative test, and then sometimes I think more often than I would have liked to, students just stop there and they say that local minimum is 1/2, local maximum is minus 5. But these are just locations of local maximum and minimum. To get the value of the functions maximum and minimum, you need to take these x values and insert in the function, and then you're going to get the value. So that's how, for instance, this is how the picture looks like. So if we were to illustrate this graphically, we see that 1/2 is here, so x1 1/2 is here, and x2 minus 5 is here, minus 5. And indeed, we see that at minus 5, we have a local maximum. So minus 5, it shows that there is a peak right here, and it's very, very close to, well, in this scale, it's a bit close to 0. I hope you see that right here. When x is equal to 1/2, we have a clear bottom here. So that's local minimum. So here we have local maximum. And here we have local minimum. And now we know these values. So that around here we have approximately 62.2, and around here we approximately have 6.7. So these are the approximate values of local maximum and local minimum. All right. So this was strictly by following the recipe, finding derivative, finding critical points, classifying by using second derivative. So clearly second derivative is negative, that's concave. Second derivative is positive, that's convex. So what about global maximum and global minimum? Can you tell me something about global maximum? Does it even exist here? So what's the, yeah? No, of course, yes, no, because if we go along x-axis, it's just gonna shoot up like this. If we go to that side, it's just going to decrease infinitely, to minus infinity. So again, by using derivatives, we picked up local maximum and local minimum. That's as much as we can do. However, I wanted to continue a bit on this example for a minute. What if I tell you an additional condition? So we do all of that, we do the derivatives, we find the critical points, we find local maximum, local minimum. But what if I tell you that instead of looking at all possible x values, I'm only interested at this function, let's say from minus 6 and until 4. Right? So let's say I'm only interested in maximum and minimum points when I look at x values from minus 6 to 4. I'm not interested anywhere else. So when I made this extra condition, I can maybe say something about global maximum or minimum now. So when function is at 4, it's right here. It's around 100. According to this graph, it's about 100, a bit more than 100. At 6, it's somewhere here. So it's still smaller than 62. So when I additionally give you an interval that I want you to look at this function, then you also should check the boundaries of that interval. So if I tell you, find local maximum and minimum, or maybe even global maximum or minimum of a function, like this, on the interval from -6 to 4. Then, as always, you start with your critical points. And we found one critical point at -5, another one at 1/2. So these are within the interval. So this is local maximum, this is local minimum. But now I can say something more about global maximum. So in this interval, the absolute highest value the function can get is right here. And note that this value is bigger than this value, which was our local maximum. So at the boundary of interval, here we actually find global maximum. So you can always find global maximum or minimum if I'm restricting the interval over which I consider this function. So we find the local guys here. At -6, well, this value is not bigger than the local maximum, so local maximum stays, local minimum stays, and now we found that this is global maximum. And actually, within this interval, from -6 to 4, this is actually global minimum. Because in this little interval from -6 to 4, this is the lowest value the function can get. If we look at all possible x values, we don't know. It goes like this, or it goes like this. So there is no global maximum or minimum. But when we restrict our attention to a specific interval, now we actually can say something about global maximum or minimum. So here we have global maximum, and what used to be local minimum, it became global minimum. So we can write this down. That, global minimum if we consider x values from -6, from -6, 4. So if we consider x values only in this restricted interval, then what used to be local minimum became global minimum. And it gave us a new maximum, which is global maximum at this point. So to append this example, we can write this. If we consider f of x at a specific interval, we evaluate f of x at boundaries of that interval. So for example, from -4 to 6, I'm going to evaluate at -4 and 6. Interval to check for additional candidates of maximum or minimum. And as we can see, those can become global maximum. If I had considered all x values, there is no global maximum or minimum. But at a restricted area, there is. If I look at corner points. All right, let's look at example 2. Again, we're going to do exactly the same. Yeah. Yeah. All right, so let's have example B. Again, we're going to do exactly the same, just different function. F of x equals x times logarithm of x. Okay? Find local maximum or minimum. So before handling the task, we do not know whether it's going to be maximum or minimum. Many things can happen. So again, we do the recipe and we take the derivative of this. So I need to find a derivative. So what's the rule that I'm going to use? I'm going to use product rule. U of x, v of x. Okay, so the derivative of u of x, that's just going to be 1 times logarithm of x. So this bit is u of x prime. This is v of x as it is. And then I add u of x as it is, x. And then what's the derivative of logarithm? 1 over x, exactly, 1. Okay, so that is convenient. I have logarithm of x plus 1. So that's the derivative. Okay, so now I need to solve for x value, which makes this derivative to be equal to 0. So logarithm of x plus 1 equals 0, or logarithm of x equals minus 1. So I need to solve for x in here. Do you remember how to solve this equation? How should we proceed? There is a trick that we learned, how to get rid of logarithm. Yeah, you know? Or no? Yeah. Yes, so the way we do it, so if this is equal to minus 1, if left-hand side is equal to right-hand side, then it must be that e raised to logarithm of x is equal to e raised to minus 1. It must be. But we know that e raised to logarithm of x, we know that all of this is just x. So all of this means that x is equal to e minus 1. So that's the critical point. So in this little equation, we needed to remember properties of logarithm. That if logarithm of x is equal to a certain number, if I write them as powers of e, the equality still holds. But now we can just write e to the ln of x as x. That's the standard trick. Okay, so that's our critical point. That's our critical point. And now we take the second derivative. We need to classify. So let's do that quickly. So that was logarithm of x plus 1. What is the second derivative? So what is the second derivative of logarithm of x plus 1? It's just 1 over x. Because derivative of this is 1 over x by the standard rule, and derivative of this is equal to 0. All right? So now, if we insert e to the minus 1, I have 1 over e to the minus 1. That's the same as e. And clearly e is 2.71 many, many numbers. Positive. So we have that the function is convex. Which means that we have a local minimum at e to the minus 1. So let's take a break, and then we will evaluate the function of this, and we will continue.